Good afternoon, everyone. So you saw I posted the final project, right? Any questions on that? Okay, great. So the last material that will be useful for the final project is this unit, which we should be able to cover this week. So at that point, you'll have everything you need for everyone to dive into the final project. Of course, people who are going to tackle the neural networks or the linear methods can already start the project. But those of you who want to do the tree methods, that's what we're going to talk about now. Okay, so the first thing we're going to talk about is the idea of ensembling, which is basically combining several methods together to improve the performance beyond any single method. So just as a way of starting with some intuition, let's say that our goal is to determine the heavy side of a biased coin. So we're just trying to say, is it heads or is it tails? And let's say we don't know it, but it turns out that the heads of this coin occurs 70% of the time and the tails occurs 30%. So let's say that we flip the coin n times and choose the majority vote. You know, how often will we correctly predict that the heads is the heavier side? So if we do this once, obviously, 70% of the time it's going to come up heads. We choose heads, and we're correct 70% of the time. But if we do this 11 times, and we again choose the majority vote, so 6 votes or higher out of the 11, then you would find that you're correct 92% of the time. And if you do this 31 times, you're correct 99% of the time. Okay, so if you're curious about how these numbers can be computed, they come from the CDF, the binomial distribution. The details are not really that important to us. But essentially, what's happening here is as we're doing more and more independent trials of this coin flip, the uncertainty the variance is reducing. And eventually we will converge to, with very high probability, the correct answer. So the reason we're describing this example is that it's quite similar to a classification problem. If we think about this as a binary classification problem, and instead of 31 coin flips, let's say we have 31 classifiers. Each of those classifiers are not so great. They're only correct 70% of the time. But if we can somehow do a majority vote of those 31 classifiers, we will be correct with 99% accuracy, right? So that's kind of the motivation. We can now these individual classifiers, they are referred to as weak learners, and when they're combined, that classifier is going to be called a strong learner. That's just the name in this literature. So this whole procedure is called ensembling, when you bring together many weaker classifiers to try to build a stronger one. The key, though, the part where this falls apart a little bit is that for these results to hold, we need that the classifiers are all generating statistically independent outcomes, right? Because imagine that I had the same classifier exactly, and I ran it 31 times. I would get the same answer 31 times. Majority vote, wouldn't change anything, right? So what we're really exploiting here is statistical independence across coin flips or across classifiers. And so the question then is, well, how do you do that in practice? You're given, one data set. How do you make different models which are going to act more independent? Okay, so there's a whole bunch of different ways to do this, and that's what we're going to start talking about. And we'll just start really simple. So the first topic is these things called voting classifiers. So we sort of saw a picture or an example of a voting classifier on the previous page. So if we have an ensemble or a collection of base classifiers or weak learners, what we described on the last page, the hard voting classifier takes a majority vote. Now, if your base classifiers provide soft outputs, meaning like probabilities, not just 0 or 1, then you can do actually better. What you can do is you can combine those probabilities. If you think about the classifiers as giving you a PMF, you can just average the PMFs. You get a new PMF, and then with that new PMF, you can take the peak of it to see what the to make a prediction. So that's called the soft voting classifier. So that tends to work better than the hard voting classifier. And all this stuff is implemented in scikit-learn's voting classifier method. So again, this voting classifier is going to work well if and only if those base classifiers act in a somewhat independent way. You could say if they're sufficiently diverse. So there's a couple different ways you can try to make these classifiers diverse. The first way is if you have a common prediction model. So for example, maybe they're all logistic regression, but you train them using different data sets. There's different ways to do this, but one way is if you have a data set, you split it up into non-overlapping chunks, partitions, and you give each chunk to one classifier. And so now these classifiers are all going to be a bit different because they were trained with different data, so they're going to make somewhat different predictions. And you can ensemble them, and maybe this will work better. Maybe not. You have to be careful how you do this. Not all of these methods are going to be successful, because if I want to make 5 classifiers and I give each a fifth of my data, well, those individual classifiers are going to work worse. So that's probably not a recommended method, but there's other ways, as we'll discuss, there's other ways of using a common data set and giving it to the individual classifiers. Okay, another approach is to use different prediction models, but a common data set. So for example, maybe one of the classifiers could be logistic regression, another could be an SVM, another could be a neural net. These classifiers, even with the trained with the same data, are all going to act a little bit differently, so they're going to have a bit of diversity. And hopefully, if you ensemble them, you see some gain over using any of them individually. And now there's actually another way of doing this too. So even if you still want to use logistic regression in all cases, what you could do is you could train different regression models that are restricted to different subsets of features. So this makes sense if you have lots of features. If you have lots of features, maybe you can reason you don't need all of them. So you can take different random subsets and give that to different classifiers, and maybe they'll work. Maybe this ensemble will work better. Okay, so those are just some sort of basic things we can do. And although we focused on classification here, everything on this page could be repeated for regressors except for this voting stuff. For regressors, it would be simpler. You just get continuous outputs and you could just average them. Okay, so that's it's just sort of an introduction. Any questions on any of these ideas? Okay. All right, so now coming back to the idea of data diversity, the method that I described before is actually called pasting. So if I have a complete data set and I want to train, let's say, 5 different predictors, what I could do is I could split that data set, I could partition it to 5 non-overlapping subsets, and I could train one of my predictors with each. So in this case, each sample in the data set is used exactly once by one predictor. And so another approach that tends to work a bit better is called bootstrap aggregating, or short bagging. And the idea behind bagging is that you draw samples with replacement. It's kind of a counterintuitive idea, but it goes like this. So for that first classifier, imagine I have this big data set. Instead of taking a fifth of it, I draw one sample, give it to the classifier. Then, without taking that sample out of my full data set, I take another sample. I might have picked the same sample twice. Could happen. And then I take another sample and so on. And there's samples that I'll never pick. You know. And then I move on to the next class where I take, again, I sample with replacement. So in other words, each of these samples could be used multiple times by different predictors, or some of the samples might not be used by any predictor. But it turns out that this second approach, bagging, usually does work better than pasting. Okay, so a little bit more detail on bagging. So typically, if n is the total number of training samples, like always, then you tend to draw n samples per predictor. And it turns out that when n is large, you can show that approximately 1 over e, or 37% of your samples, will never be used by a given predictor. So if you have n samples in a data set and you draw n with replacement, about 37% won't be used. But that doesn't mean they're wasted, because those samples that are not used by, let's say, the first predictor can be used for cross-validation. And they call those samples the out-of-bag samples. So you don't use them for training, but you can use them for validation. Now the next predictor is going to have its own subset of training. Approximately 37% of the data set it won't use, but again, those can be used for cross-validation of the next predictor and so on. Okay, so these things are implemented in scikit-learn's bagging classifier and bagging regressor methods. And if you want to do bagging, you set bootstrap equals true, and if you set it equal false, then it will do pasting. And if you want to do out-of-bag cross-validation, then you set OOB score equal to true. Okay, and these methods, these scikit-learn methods, you just give it a list of predictors. It could be any scikit-learn predictor. You can give it, and it will combine them, any set of predictors this way. Okay, so that's bagging and pasting. Any questions? Yeah.
So would the reason that pasting tends to work less well is because if you're doing it without replacement, aren't you? I'm guessing the mechanism is you're technically changing the probability of each of those samples, whereas with bagging you're not altering the normal probability of each of the samples.
I think I don't know exactly what the answer is, but this is what I think. Notice that you are drawing n samples per predictor. So if I have many predictors, which is what tends to use well, like let's say even if I have 3 predictors, if I have to do pasting, then I'm only going to get, each one will only see a third of the data set, right? If I do bagging, it'll see 63%, even with 3. Now if you go to 10, it's like 10% versus 63%, and so on. So I think that's probably why, is that they see more samples. But there's probably other reasons. I'm not sure exactly what the literature says. Yeah.
Do you always use an odd number of predictors?
If you're doing voting, then it helps break ties. If you're not doing voting, there's no reason to. Yeah. Okay. Great. Any other questions? Okay. All right. So we've talked now about like how to split up data and feed it to different predictors. You can also, we said, split up features. So using random subsets of features for different predictors. So there's different ways of doing this. If you just have a few features, this is probably not a good idea, right? Because if you just have a few features, probably a subset of those features are going to be really important. And if you have a predictor that doesn't see those important features, it's just going to do terrible. But if you have many features, then this is a good approach. So if you have, high dimensional data. So the idea here is you could, again, sample features with replacement, bootstrap, or not. So you could, if you have 30 features and 10 predictors, you can give each one 3. Probably works better to give each one 63%, with that bootstrap method. Now you could combine these ideas. You could combine the bagging and pasting with random patches and random subspaces. And so if you use both random data and random features, that is called random patches. And if you use random features but full data, that is known as random subspaces. So just a bunch of jargon. But those are the ideas. Essentially, you have 2 ways to make predictors diverse. You either train them differently or you give them different subsets of features. Or you make them structurally different, like a different architecture. Okay, so that's all I have to say about this sort of high-level ensembling. Any questions? Okay, so now let's take a complete turn and discuss something totally different, which is a new type of building predictors that we haven't seen before. And it's actually a really nice way to do it. It's totally different from everything we've seen. And it's called decision trees. So these things can work. They're very general. They can work for regression or for classification. In fact, we can talk about them for both applications more or less at the same time. So the main approach could be at a high level, can be summarized into 2 steps. First, we partition our feature domain into L regions. And then second, we output a fixed number, ZL, whenever the test sample is in the Lth region. So let me give you a visual example. So in this picture, I have just 2 features, x1 and x2. And this is the output vertically. And you can see that whenever x1 and x2 are in this region, we're outputting that value. Whenever x1 and x2 are in this region, we're outputting this value, and so on. So you can see there's 1, 2, 3, 4, 5 different regions, and all those regions have different outputs. Okay, so it's kind of like a lookup table sort of thing. You get a test sample, you figure out which region does this belong to, and then you say, oh, if it's in that region, I just give this output. Simple as that. Here's another picture of the regions. If you're looking from the top down, you have x1 and x2, and here you see region 1, region 2, region 3, 4, and 5. Okay, this is just an example with 2 dimensions to visualize it. In general, you use these with much larger numbers of features. So, okay, any questions on that very high-level idea? Yeah.
Does region have to be a parallel one, or?
Do they have to be parallel? Did you say what? I didn't hear.
Yeah, the separate two separate region, could it be decided to the same output?
Can the regions overlap? Is that what you're asking?
Um,
I still don't understand the question.
It's like in the picture, we have R3 and R2 and R4. Can they have the same output?
Oh, sure. Yeah. You could have the same output for different regions. Yeah. Now, we're going to talk a lot about how you construct the regions, but let's say if the regions were fixed and given to you, one way that you could see to set the output would be, if you're doing regression, you could just set the output in the Lth region as a sample mean of the targets corresponding to that region. So it's like you have your training data set, you look at all the samples that fall here, you look at those corresponding targets, and you compute the sample mean of those targets, right? And that would be a good output for things in that region. Over here, this corresponds to a different subset of your training data. You figure out what is, for those targets, what is the sample mean, and that would be the number you output for any test samples that fall into this region. Okay, so it's pretty straightforward, at least in terms of regression, how to do that. For classification, we can't do that because, if let's say I have binary zeros and ones, I can't take the average of zeros and ones because I would be reporting a value that's not a valid class. I can only report 0 and 1. So instead of using the sample mean, you could use the sample mode, which is the most common value among the training labels that correspond to that region. Okay, so with a slight change, you can make this work for classification. Okay, so we're going to talk a lot more about this, but that's sort of just to start. Any questions so far? Yeah.
I have a question about bootstrapping.
About bootstrapping, sure.
Yeah. When we sample with replacement, if we take the same sample twice, during training, do we calculate the loss twice for that sample?
I think so, yeah. Yeah, you would just calculate the loss. It would count twice.
Okay.
I don't think you do any modifications.
If we pick the same feature twice in feature bootstrapping, does that mean, like, what does that mean? That do correlated?
Yeah, that's a good question. So I'm actually not sure how scikit-learn implements that. In some methods, in practice, it certainly is possible. It's possible to have very correlated features, and so some methods are going to be more or less robust to that. So we saw things like ridge regression. There's things we can do if we have correlated features. So my guess is that in scikit-learn, they don't like trim the feature list if a feature is repeated twice. My guess is they just use it twice. Yeah. But I don't know exactly. It's a good question. Okay. Okay, great. So any more questions so far about the trees? Yes.
Partitioning the data into rectangular shape, is there any chance that we need to partition the data in other different?
That's a great question, and we are going to talk about this next. So at a high level, the answer is, we could use different non-rectangular shapes, but the main strategy that's used in almost all cases results in rectangular shapes, and I'm going to describe the strategy now. So how do we construct these regions? We want to do this in a very efficient way, efficient for training and for test. And so essentially, it's based on recursively partitioning the feature space. What I mean by that is maybe the first thing I do is I split the feature space in half, left and right. Now, for the left half, I split that in half. So I have up, down. On the right side, I split this in half. So now I have these two halves. And then for that last part, maybe I split that again in half. So that's what I mean by this recursive partitioning. We split again, and so on. Of course, at some point we stop. But that is part of the reason that we have regions of this shape. And the other reason is that when we split, it's common to threshold a single feature at a time. So in this first split, this one, in order to make that split, I said, let's threshold x1. If x1 is less than some value t1, that will partition my data one way, and if it's greater, that's the other way. And then for this, I then say, okay, I'll further partition this subset based on x2. If x2 is greater than t2, that will be one part or the other part. And so because I'm just using one feature at a time, it means that the boundary is always going to be perpendicular to one of the coordinate axes. And that's why we get all these square rectangular patches, regions. Okay, and that's just to make things fast and simple. And the reason for this simplicity sort of comes when we say, well, okay, how do I actually determine these regions. So we're going to do a lot of sort of brute force searching. And if I have to just, when I do my brute force searching of how do I figure out, okay, first question is, I start with my full data. How do I figure out what that first partition is? So now I have a whole bunch of features. I have to go through my features one by one to figure out which is the best feature to split. But when I consider each of these features, I have to consider all possible thresholds too. So, here there's sort of a lot of work to do. So if I can just do one feature at a time and one threshold at a time, this becomes feasible. If I have to do some very complicated search jointly over multiple features with a very strange boundary, that would just be overwhelmingly complicated. So that's why just looking at one feature at a time, one threshold at a time, it makes this whole process tractable. I think that's why it's done. Okay, so that's kind of an explanation for why the regions look like this and overall how we do it. And this overall approach is called a decision tree. So once we have decided on the sequence of which features to look at and the particular sequence of thresholds, then given a new test sample, it's very easy to classify it or to predict on it. You simply look at your test sample, first feature, look at that. If it's less than a threshold, you go down this branch of the tree. Then in this case, you look at the next one. If it's, maybe it's greater than that threshold, you go down this side. And after just a few steps, you know which region you're in. Now that you know the region, you just look up in a table the output and you're done. It's extremely fast. And it's very explainable too, right? It's very clear. If you had to explain to someone, how does your predictor work? This is the clearest possible explanation you could give. Well, if you do this, this happens. If you do this, this happens. And it's crystal clear. Unlike a neural network, if you ask someone, how does your neural network work? I have no idea. There's tons of weights in there. They're doing all this crazy stuff. Came out with a good answer in the end, but how do you explain it? And there's actually many applications like in finance and insurance and stuff where there's laws that say the model needs to be explainable. And so these sorts of methods are very useful in that situation, whereas a neural network, they'd say, you can't explain your predictor, so it's not fair for you to use it. If you have to deny someone insurance and they sue you or something, and they say, why did you deny me insurance? Well, if you have a scheme like this, it's very clear. You can explain it this way, but if you say, well, it's my neural network did it, it doesn't sound so good. So so that's why these are decision trees, this particular way of doing it. So a bit of terminology. The root of the tree is the part which is the entire domain of the features. So that's just here it's the top. And then the leaves of the tree are the decision regions. So we start with the full data at the root, and we break it down into these decision regions, and those are the leaves. So sometimes we refer to regions, sometimes we refer to leaves sort of interchangeably. Okay. Yes?
So as you get more leads in the dimensions, will say it's like a regression template eventually map to whatever
So how complex can you make this?
Yeah.
Yeah, the deeper you make it, it can be more and more and more complex. So basically, no matter what training data set you have, you can pretty easily make a tree that perfectly predicts your training data. So as we'll talk about, this is one of the weaknesses, they overfit. And so there's different strategies people use to prevent this overfitting behavior, because it's very easy for them to perfectly predict your training set. You just have to have enough levels until it sorts all your training samples. Okay. All right, good questions. Any other questions? Okay, so let's talk a little bit more about how we train the tree. So they're trained in a top-down manner, which basically means we figure things out. We first figure out this. In other words, figure out which feature to threshold first and what is a threshold. Once we've decided that, then we figure out the next level. Once we've decided that, we figure out the next level, and so on. So, as usual, let's say our data set are pairs of xi, yi, and let's define an index set. We'll call it S. This starts out just being the numbers 1 through n. So we can, S is basically, it tells us, some subset of our training, and we're starting with all the training data at the top. So what we're going to do recursively is we're going to do this over and over, but the first time we do it, we're going to split S into 2 subsets. We'll call it S1 and S2. And our goal in doing this is to figure out how to split it by choosing some feature and some threshold so that the labels are most homogeneous or similar within each subset. In other words, once we split our training data into 2 parts, we want that within the first part, the labels are very similar. Within the second part, the labels are very similar. That's our goal. How do we make those 2 sets of labels most similar within each subset? And so now we can handle ordinal and categorical features pretty easily here. If we have an ordinal feature, we just split based on a numerical threshold, call it T. So this is like subset 1 are the training indices I such that this is for some feature J such that the samples for that feature are less than T, and then subset 2 are the training indices I for which our training training data for feature J is greater than T. So this is just how we do the split. Now, if we have a categorical feature, obviously we can't compare the categories to thresholds, but if we have a finite number of categories, there's a finite different ways we can, split that set of categories into 2, right? So we would just figure out all those different ways to do it, and we would basically look through them one by one. So if I have categories A, B, C, D, I could do, this is one way I could split it, A, C, B, D. I could also do A, B, C, D. I could do A, B, C, D. There's a finite number of possibilities. Okay, so now importantly, to find the best split, we just search jointly over the feature and the threshold. And this, as you can imagine, this can take a while, right? Start with this feature, consider all possible thresholds. Now, if I have n training samples, it's not like I have an uncountably infinite number of thresholds I care about. I only care about, a particular threshold that splits my training data. So if I have n training samples, there's essentially n minus 1 thresholds that I care about, because there's n minus 1 different ways I can split that scalar feature, or the training data for that scalar feature. Is that making sense? We'll see an example on the next page. I think it'll be clear then. And we also talked about homogeneity, but how do we define that? There's actually many ways to do it, and I'll show you some examples later. Anyway, so once we've decided on that first split, we've decided we're going to split x1 according to t1. Now we have s1 and s2. Now we just repeat the procedure for s1. We split s1 into 2 parts. And then later, we'll split s2 into 2 parts, and so on. We'll use exactly the same logic to do it. Exactly all of this. Okay. Eventually, we're going to stop. Okay, so one way to stop is if the labels are perfectly homogeneous, or sometimes people will write pure, within a subset, if all the labels are the same, then there's no more splitting to do, right? If you get down to one sample, there's no more splitting to do. Now, sometimes people don't go that far. Usually they don't. Usually they might say stop when the subsets have a minimum number of samples, maybe 10 samples or 100 or whatever. Or they might say only go down to a fixed depth of like, 5 levels deep. Don't ever go deeper than that. So there's various things you can do to to basically stop this training procedure. And by doing that, you basically prevent overfitting. If what you do is you just go until you can't split anymore, so every one of your regions has one training sample, then you've essentially perfectly fit to that training data set no matter what, and probably not going to do that well on test data. Probably overfit. Okay, so that's the method. Let's look at an example. I think this might help to explain it a little bit better. So in this example, we have two features. So age and car type are the two features. So this is an insurance example. Our goal is to predict whether a given driver is high risk or low risk. And we have two features to work with, the driver's age and the kind of car they're driving. You can see that the car type is a categorical variable, whereas the age is an ordinal variable, and here's the binary label data. There's n equals 6 samples. And so the first thing we have to do is to train the tree, you have to decide at the top level, are we going to split based on age or based on car type? So let's consider what happens if we hypothesize we're going to split on age first. So the next thing we have to figure out is what is our threshold. So to make this data set a little bit more interpretable, let's order the age numerically because it's sort of shuffled here. So we have a 17-year-old, 20-year-old, 23, 32, 43, and 68. And let's look at the class. So for 17, we have high risk, 20, high risk, 23, high risk, 32, low risk, 43, high, 68, low. Okay. So let's say I'm going to consider splitting by age, and now I need to choose my threshold. How do I choose a threshold so that after I split, I'll have the samples within the two classes are going to be similar, as similar as possible to each other? Okay, so you can see that there's really only the number of thresholds we have to consider. We can either threshold between 17 and 20, in which case we get those two, or I can threshold between 20 and 23, in which case I have those, or I can threshold here, or here, or here. All right, so do you see how I really only have 5 thresholds to consider? Because there's only essentially 5 ways to split this single feature. Okay, so what do you think? Maybe I'll get back to the attendance calling. What threshold would you choose? I'll ask. Let's see. Harry Landwehr? Yeah. So.
Between the 23 and 32, that's where our class starts.
Yeah, I agree. That would be a good place because here you have a totally homogeneous, and here you have almost totally homogeneous. If you would have chosen this, then this would have been worse, right? They're less homogeneous. If you'd chosen this, this is homogeneous, but this one is even less and it's bigger. So yeah, I think this is the best way to go. If we did this, we could repeat this with using car type, and we could use similar logic. We have to consider these 3 types of cars and different ways we can split it. That is another possibility to start splitting with car type. But however, they decided to start splitting with age here. And you can see that the value of the threshold was exactly in between 23 and 32. It was 27.5. Okay, so that's essentially that very first partitioning, that first decision. And the nice thing is now, if a driver's age is less than 27.5, you will just predict high risk no matter what. Okay, done. There's no more splitting to be done here. On the other hand, if the age is greater than 27.5, we have some more work to do. So now we can consider the car type, and let's look at those three drivers. We have a 32-year-old, so we have a truck, 43-year-old sports car, and 68 family. And so essentially, yeah, these are the samples we're considering now. And you can see that two of them give a low risk, the other gives high risk. So my last decision is going to be if the car type is sports, I predict high. Otherwise, that takes me down this branch of the tree. And in that branch of the tree, this is totally pure, it's low. So essentially I'm done. There's no more splitting to do here. We've perfectly handled this. We've perfectly fit to this training data set. All right. But hopefully you see a little bit more about this, this procedure about how we train. Any questions? Is this making sense? Okay, great. So now we can get into some details about exactly how do we define these homogeneity metrics. So if the goal is to maximize homogeneity within S and within S2, S1 and S2, we could also say the goal is to minimize inhomogeneity or like inconsistency within S1 and S2. And so let's first consider regression. So in that case, we have continuous, real number labels. We could measure inhomogeneity by the variance after our split. Because the higher the variance, the less samples are similar, the more they're different. So how would we compute that? Just, it's exactly how you would think, but just to establish the notation. So we have two subsets, S1 and S2. We'll use the variable L to index a subset. It's either 1 or 2. The first step would be to compute the sample mean in subset 2. So for this, what we do is we first say, let's sum up the targets for the indices I in S, let's say we start with L equals 1, sum up the targets in S1, and then divide by the size of S1. So that's just the sample mean within S1. We repeat that for L equals 2. Now we have two means, mu1, mu2. And now we can compute the variances. So this is just the standard sample variance equation. Here we're looking at the deviation, the squared deviation from the sample mean. And so this is going to give me two variances. We could use an unbiased estimate. Here we're using the biased one. At the end of the day now, we have two different variances. The variance in S1, or the variance in one subset, the variance in the other subset. But we need a single number to basically say, is this going to be a good split or a bad split? So we can average the variances. And we want to average the variances according to the relative size of the two subsets. So, if one subset is really small, its variance should count less than a subset that's really big. So, so these ratios, this is just the proportional size of subset 1 and subset 2. We're using that to average the two variances into a single variance V. So now that we have this V, I can simply move the threshold, from very small to very large, and I can measure the variance after splitting. And when I see the smallest variance, the smallest average variance here, that would be the threshold I choose. Simple as that. Is that pretty clear? Any questions on that? Okay. We could also use absolute error instead. This works a little bit better if you have outliers in your data. And we'll see a more sophisticated metric when we discuss XGBoost in the next lecture. But this is just some examples of homogeneity metrics for regression. Okay, what about classification? So in classification, let's say we have k different labels, so k different possibilities for a label. So our labels will say our integers 1 through k. And for each subset, what we could do is we could compute the empirical label PMF. So that would be a list of numbers, PLK, so here I'm fixing L, so for subset 1, I'd have a list of numbers P1K, where K goes over the different possibilities of my label. And to compute that PMF, all I do is I sum up, in that first subset, I would just count how many times does the label equal K, and I divide by the size of the subset. And I do that for each possibility of K. Now I'm going to have a PMF, set of non-negative numbers such that when I sum them, they sum to 1. Once I have that PMF, from there I can build sort of any metric I want in terms of homogeneity. Probably the most popular one is this Gini impurity. So what you do is, again, you have this weighted average, just like we saw on the previous page, but we're weighting these terms. These terms are constructed like this: 1 minus the sum of the squared PMF value. So let's think about this a little bit more. Let's think about the extremes. In the extreme that I have a completely pure subset, what does a PMF look like? So we have something like this. This is going to be P, LK versus K. Let's see, Sean start? So if I have a totally pure subset, what does this PMF here look like?
Just
So let me maybe give you a specific example. What if all the samples are 2? All the labels are 2. So you think it's a straight line, or? Okay, so what we're gonna have in that case, we're gonna have a spike, right?
Yes.
That's what we're gonna have. So it's gonna be a spike. So it basically says with probability 1, all the samples are 2, and with probability 0, probability 1 you get a sample of 2, with probability 0, sample of any other K. Okay, so that's an extreme value. So what happens now if you plug that PMF into this expression? What number do you get? You're just summing the squared values, right? So this is going to be 1. So if I sum the squared values, I get 1, right? 1 minus 1 is 0. So that is one extreme. There's no way that this quantity can be any less than 0. So when you have total purity, this Gini metric IGL is exactly 0. Okay, so the next question is, what is the opposite extreme? So let's see. Is Juchen Yang here? Yeah. So what do you think, what would be the opposite extreme if I have the opposite of purity? I have, what do the PMF look like?
PMF.
Yeah, the probability mass function.
I've got no idea.
No idea? Okay. So the idea is if I have, the most diverse I could have is if I have equal probability for every K. So that would be like a flat line, right? Each of the values would be 1 over K. Maybe I'll do that in a different color. So with probability 1 over capital K, it's 1. With the same probability, it's 2. That's the most diversity I can have, right? It's like totally shuffled. So in that case, what is the sum of the squares going to be? So each of these, when you square it, is going to be 1 over K squared, right? And then you sum it K times, that turns into 1 over K. So this is 1 over 1 minus K. That's the largest possible you can get. So basically, these are the two extremes. And every kind of situation is going to be somewhere between these two. The Gini impurity is 0 if it's perfectly pure, or up to 1 over 1 minus K if it's absolutely mixed, shuffled. Okay, but anyway, this is just the most popular way to do your splitting metric for a classification. And there's other ways to do it. You can use entropy, misclassification error, chi-squared, a bunch of things. You can look them up in other books if you like, but we're not going to get into too many details, but this one will come up again. Okay, just sort of give you a flavor of how you can build these metrics. Okay, any questions on that? All right, so another thing you can do is, what if someone says, well, I don't care about these purity metrics, I just have a loss function. This might even be like logistic loss or something. You make up any loss function you want, and they say, I want you to build me a tree that minimizes that loss, generic loss. So this loss is some function of the true label and the prediction of that label from the ith feature vector. So here the tree, we're just denoting the tree by this function f. Okay, so how do we even approach this problem? So to approach it, it's nice to split it into two steps. So essentially, let's write our tree, f of x, as z sub qx. Okay, remember that zl is the value that we assign to the leaf or to the region L. Okay, that's just a list of known numbers. It's something I have to optimize, but it's just a list of numbers. The other thing, maybe the more interesting thing, is this function qx. It is the function that takes in a feature vector and tells you which region or leaf it lands in. Okay, so those are essentially the two things we need to think about when we design trees. The value assigned to a leaf and the decision region that assigns x to a leaf. Okay, so given that, we can now write tree design this way. So we want to minimize, we want to design both this vector of z's as well as the function q of this is the total loss. Now the loss has been split into two sums. The inner sum is saying, let's sum over all samples I such that xi ends in leaf L. And whenever that happens, I know I'm going to output ZL. So my loss for all those samples will be the loss between yi and ZL. Right. And then the only other thing I have to do is just add up over all the possible regions. This is the loss. If I land in the Lth region, now I just sum across all regions. Okay, so now we have kind of a clear design objective. This is what we want to do. Now we're not going to be able to perfectly minimize this. What we're going to do is we're going to do this one split at a time. It's a greedy approach. So just like before, the very first decision we're going to make is how to do that first split. And so essentially what we could do is we could say, okay, before I do the split, let's say in that case, I just have this full sample set S, which contains all my training samples. The loss before I do the split would look like just the sum of the loss between yi and z1. Let's say that z1 is the value I would assign just the average value. Now, after I do the split, I'm going to be able to split my data into subsets S1 and S2, and now I'm going to have this is going to be the loss if the loss for all the samples that end up in S1. And this is just a function of Z1. So now I can just do a numerical search over Z1, and I can find what is the best Z1. Similarly, I can, for all these other samples that fall into this other class, I can do a search over Z2. And so essentially, you can see that we've split this problem into designing Q, which is essentially saying, how do I do this split? And for that, essentially, we just have to choose a threshold. And second, designing Z, or Z1 and Z2 here, that's just the output value. And so this is a pretty tractable procedure. You can see, given any generic loss, you could design a tree in this top-down manner, one split at a time. It's possible. Okay, so All right, any questions on this training procedure? Okay, so that's sort of it in terms of training. Let's just reflect on advantages and disadvantages of decision trees. So in terms of advantages, these things are very general. We've really not made any assumptions on our data. We can work with categorical features, with ordinal features. You don't even need to standardize the features. Because if you scale a feature, all you're going to do is just scale the corresponding threshold. But nothing's going to really change, so you don't even need to standardize. These models are very interpretable. They're what we call a white box model as opposed to a black box like a neural network where we just don't really understand what's happening inside. Now we understand exactly what's happening inside. We can describe it to someone very clearly. And the prediction is very fast. If you think about prediction is just a matter of making D decisions where D is the depth of the tree. To get a sense about how deep a tree will be, imagine that a tree, when you train it, it splits your training data in half every time, just for sake of argument. So if it splits it in half any time, and you go as deep as you can go, you will essentially have log base 2n stages, right? Because by the time you split it this many times, you've split, all your leaves will have one sample. Okay, so roughly speaking, you may not go that deep. You might not have be splitting things perfectly in half at every time, but on the order of log base 2n decisions are required to process a test sample. So even as n grows to be really large, log base 2n grows very slowly. So it stays very manageable. So those are all the advantages. In terms of disadvantages, okay, training can be expensive if every feature is considered for every split. Like if you have a lot of features and you have to go through them one by one and figure out exactly how to threshold them, that can be expensive. So in practice, people don't actually do that. They take shortcuts. They consider only a few randomly chosen features for each split. It's not really essential that you get exactly the perfect feature at every split, because if not, you'll just split later. Another issue with trees is that they're prone to overfitting. They're also, from one perspective, highly dependent on your training data. You can imagine a case where you change one training sample, and that will have a ripple effect and cause every single decision of your tree to be different. It can happen. The way you tend to regularize this is you enforce a minimum number of samples per subset, a max depth of the tree, and so on. And as you do that, your trees become more stable, less prone to changing. There's a really nice overview of decision trees in the sklearn documentation. You can click on this link if you want to see more. So that's it. That's all we're going to say about trees. We're going to get into some very specific. Next thing we'll do is we'll combine ensemble methods and trees, because this is a very, very common thing to do. The most common trees today are all ensembles of trees. So we'll talk about that next time. But hopefully you can see that decision trees are a pretty neat way of doing prediction, quite different from anything we've seen before. All right, see you guys on Wednesday.
Yes.